Alright, welcome to the video on graphing quadratic functions. Now the two problems that I have here are problems that we've been discussing in class together. And so you may already have these problems done, but I did want to review kind of the concepts we talked about in class for you, have the opportunity to review them and therefore ask more questions if you have them. And so I got to kind of set up. The remainder theorem is what we've just got done with. We just studied that, and the purpose of studying that was the method of plugging numbers into the function and graphing them rather quickly, as opposed to trying to figure it out mentally and the possibility of mistakes. And so I've set up both the remainder theorem for 1 and 2. I'm going to work problem 1 first, and more importantly, going to discuss this part about domain range increasing and decreasing. So the reason why we plug in numbers is I personally believe that in order to understand how a function is generated or the graph of a function is generated is that from just plugging in numbers. And so I'm not going to plug in 0 into this the remainder theorem because the nice thing about plugging in 0 into a polynomial is it generally is the last term in the polynomial, or the one with x is 0, because if you know it's 0 times 0 squared is 0, so it's going to eliminate all these terms with x's because it's going to be 0, and so the last thing left over is 6. Okay, I apologize for a little a smaller graph, but just the way I copied in. So if I plug in 2 into this particular function for number 1, I get 2. 2 times 2 is 4, and I'm going to work this rather quickly because this is a concept that we've already talked about, and if you need to review it, it is on the previous sections. We plugged in 2, we get negative 2. If we plug in 3, let me quickly erase this here. Again, the nice thing about the remainder theorem. If I plug in 3, I get 2 times 3 is 6, negative 2, negative 6, which is 0. Now in this case, let me graph these real quick. 1, 2, 3, 4, 5, 6. And then we have 2, negative 2, 2, negative 2. And I also have 3, 0. Alright, so I've given you some points to plug in, and I've left you 2 open spaces to kind of test out some ideas or some possible points. And so my recommendation to you is that if you are in this circumstance to choose a number to plug in, we probably want to stay away from plugging in negative numbers, because I'm assuming that the graph kind of appears in this area right here. So I'm going to plug in, let's say for example, negative 1, and again rather quickly I'm going to get this done here. So if I plug in negative 1, I get, let's see, negative 2, negative 10, 10, 16. Ooh, there's something wrong there. What did I do wrong? Let's see, negative 2, negative 10. Oh, I broke the rule. I plugged in negative 1 instead of positive 1. Let me go back and fix that real quick. Yeah, I've just showed you why you don't plug in negative numbers. So let's try this again. Let's see, negative 6, negative 6, 0. So I get this pattern is developed. Now, I have pinpointed the vertex of this equation. So the vertex is the point at which either it goes from increasing to decreasing. There's a lot of ways to clarify it. Or it could be like kind of like the seed of the problem, meaning it's the point that I plugged in, especially in a parabola standpoint, that everything grows from it. Either it could be the lowest or the minimum or the maximum. And that's how we clarify vertex. Also, the vertex lies on the axis of symmetry, meaning that there is a kind of an invisible line that goes down the center of a parabola where things start to mirror itself. And so I was able to identify this because I noticed that they're on the same horizontal line and they're 1 apart. So I'm going to assume that this is the vertex, and therefore also make the assumption that I'm going to go 1 out and up to here because it's going to mirror that other side. So some great things about the parabola is that every single time we graph with a degree 2 polynomial, that means the highest degree, it's going to generate a parabola no matter what. Okay, now it could be a very skinny parabola, it could be a very expanded parabola, it could look something like this. So it doesn't always have to be like a nice symmetric looking parabola like this. It could be a lot of different shapes, but anytime we have a degree 2 polynomial, it is going to come out as a parabola. So the next thing we need to look at is the x-intercepts. That's where it crosses the x-axis. Well, in this case, that occurs at 1, 0 and at 3, 0. Alright, so those are my x-intercepts. Those become very important here in the coming future for us to find. The y-intercept is going to be, in this case, 6, 0, or 0, 6, my mistake. 0, 6 is the y-intercept. Now, in order to be a function, you will not have any you won't have multiple y-intercepts. There's only be one y-intercept. In this case, this is proved that it crosses the y-axis once. So there's no way that this parabola is going to come back around and go this direction. It's going to go up for infinity, and that's why I want to see. I'm going to draw this just to show that. So it goes on, increases to infinity, especially on this side. But we'll talk about the increase decreasing here in a second. So there will never be two y-intercepts because therefore it wouldn't cross or pass the vertical line test. The next thing we're going to do is the domain and range of the function. So the domain is all the x values. Do I have any restrictions in the x values? In this case, no. Okay. Now with this particular topic, I'm just kind of getting you familiar with the idea of what a domain is. It will consistently be all real numbers. Until we start studying rational functions or radical functions where we may have some restrictions of what we can plug in for x. But in this case, the domain is always going to be all real numbers when dealing with polynomials. The next thing we have is range. So we need to figure out, these refer to the y values. So the domain is the x values, the range is the y values. Now, we look at this in terms of what is the lowest y value. So if we're looking at this axis, the y value is covered from -2 to infinity. Okay, now this is interval notation, so we go from -2 on the y-axis all the way to infinity. So look at, if we want to draw kind of a dashed line here, I'll kind of draw a line here. Whoa, that's a bad line. But everything, the whole graph is above -2 on the y-axis. So if we look at that terms, we would say that the range is from -2 to infinity. Okay? So the next thing we're going to do is now discuss increasing and decreasing. Now, this seems to be the one that we have to just, we kind of get it, and then we'll kind of really familiarize ourselves with it. Understand that by drawing this axis of symmetry, we have generated two sides of the x-axis, all numbers from -infinity to 2 and numbers 2 to infinity. So when we talk about increasing and decreasing, or where the function is increasing and decreasing, we're referring to the x-axis. So the y-axis and what's happening vertically and up and down is no concern to us, except I guess when we interpret what's happening. So the best way I establish this is by understanding a roller coaster. So for example, from -infinity, so if I'm traveling from -infinity to +2 on the x-axis, what is happening during this time period? So if I were riding a roller coaster, I'd be coming down this hill, down, 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 down. So from -infinity, from -infinity, we are decreasing from -infinity. Oh, that's a bad infinity sign. Let me try it again. There we go. Best I'm going to get. So from -infinity to 2, I am decreasing from -infinity to 2. I'm not going to bring in -2. I'm not going to bring any y values. It's just specifically talking about the x-axis. Okay? And then by default, I'm actually, so the critical point or the vertex is actually going to generate kind of where I switch from decreasing to increasing. We also refer to this as a critical point, critical value. Different things like that, but we'll get into that when we get into higher degree polynomials. But now we've decreased from -infinity to 2, and so then we're going to pick up and we're going to start to increase or go up the hill from 2 to infinity. So on the x-axis, again, I'm just referring to the x-axis on decreasing and decrease and increasing. All right, so the final step, there's a lot of explanations there, so thank you for your patience. The next step we're going to look at is local minimum. So local minimum is just referring to the vertex. Now, I'm familiarizing ourselves with some common vocabulary that we're going to use in the near future. So at this point in time, we're just identifying the vertex. So is the vertex a local minimum? Now, this is actually an absolute minimum in this case because it is the lowest point on the graph. But again, we're just kind of generalizing our idea and just getting an overall perspective of things. And so the local minimum, now I asked this question in class, is this a valley or is it a peak? In this case we have a valley inside here, so it's going to be a minimum point. The lowest point on the graph is our vertex, which is 2, -2. And you'll notice that there is no local maximums. We don't want to put 0 here, we just want to put none. There is no local maximum because these things go on forever in both directions. Now, with the essence of time, I am going to kind of end it here. I know I had another problem to work, but I think we have a general idea of things. Go back through and watch it again, and see if you can get the problem. We're going to go over this one in class number 2, and so continue to ask questions, continue to work through things, and you'll get the grasp on things. So thank you very much, and see you in class.